Good afternoon, this is Schweitzer, and we are looking to add in a second video involving mathematical calculations taking place with KSP. Now, piggybacking on the last video, we highlighted a couple of types of chemical reactions, I should say type of mathematical problems, and these are just basically going to look something like those. All of the stuff we did will just be ice table calculations with a little bit of solubility mixed in with it. Applying those things to solubility. But I want to highlight these particular types of chemical reactions so that you can see an example of them. A certain temperature chemical AgCl is added to distilled water, creating the solution. The concentration of the chloride is found to be this. Okay, so let's write out the equilibrium expression, the KSP expression. So when we do KSP, you should be aware that we're going to use this chemical reaction. AgCl goes to and comes from Ag plus Cl minus. Now again, we use this so the KSP expression, KSP equals the concentration of Ag plus times the concentration of Cl minus. We use it this way because if I did it the reverse way, which means it looked like this, Ag plus Cl minus produce AgCl, then it would be KSP equals 1 over the concentrations. In this situation, as mentioned before, people in industry just wanted the concentrations or the molar solubilities, how much is going to dissolve per liter. They want this to correlate to this. As these are bigger, this is bigger. So these two things correlate. So they decide to use this version of the equation than this one. Right? So write the KSP expression. And this is going to be called KSP. This is the KSP reaction, KSP expression. This would not be KSP. It would just be the reverse of that. So we got that one done. It's right there. What is the concentration of silver ion? Okay, so if I were to draw a little beaker of this out, you'd note that as I dissolve, I'm dissolving AgCl. Every time I dissolve, I get one of each. Alright? And therefore, if this is 1.24, then the Cl is also 1.24. E to the negative fourth. Now, they're giving me these concentrations, and this should be noted that this is the concentration at equilibrium. It's the maximum amount that would get dissolved. So that's an equilibrium value. Look at the KSP. So I'm going to use this equation. Initial stoichiometric ratio end, not playing a role. 0, 0. So I'm dumping it into an empty beaker first, just water. Alright? And then I'm going to gain x of this. I'm going to gain x of this to give me x and x. I do know the x. X is this. So it's going to be KSP equals x times x, or equals x squared. And therefore, x is this. So it's 1.24 e to the negative fourth squared equals, grab your calculator, 1.24 e to the negative fourth times 2. I shouldn't say times 2, we're going to square it. Alright, that's 1.2 times 1.2, and then we'd add 4 and 4, so this is going to be 8. So 1.44 e to the negative 8. You should be estimating and know if that answer is right. It's a k value, and the k values have no units, so it's just equals k. K value is just a number. Alright, let's go on here. So that's a pretty common example. I mean, if you're looking for a KSP problem, this is like going to be there. How would it change? If I was dissolving, let's say, magnesium chloride, then I would get magnesium ions and chloride ions, and there'd be 2 there. So I would get 2 of those for one of these. So if this concentration is 10, this one's 20. Here they're 1 to 1. Alright, so now, well, there we go. So I just given you an example, a little hint on how to solve this problem. So take a moment and pause the video and run through it and see if you can do this example. Alright, my KSP expression. The reaction I like to write out first is going to be strontium 2 plus 2Cl negative. Alright, so then we got Ksp equals concentration of strontium 2 plus times concentration of chloride negative squared. What's the concentration of the strontium ion? Well, if this is the chloride ion, this is half of that. So it's going to be 2.4 e to the negative 6th divided by 2. And that's going to be 1.2 e to the negative 6th. For the KSP. Alright, I'm going to just go the long ways, write the whole thing out. Strontium 2 plus Cl negative. Initial stoichiometric ratio, N, not playing a role. 0, 0. You can dissolve it in plain distilled water. That's why those are zeros are there. Gaining x of this, gaining 2x of that, x and 2x. And we know these values. So equals concentration of 1.2. Let's erase that. Alright. Equals 1.2 e to the negative 6th. 2.4 e to the negative 6th. Now, here's the part that really messes with people. I'm going to double the concentration. Perfect. And I'm going to square it, because that's part of the algorithm. The algorithm is not going to change. Mind you that I could add chloride from some outside source. Okay, and I still need to, okay, still got to square it. Just because I'm dissolving strontium chlorine, just because this concentration is double that concentration, that's fine. It still requires the 2. When do I double it? I double it based on stoichiometry. Sometimes that's a common question for kids. Strontium chloride. You can't memorize this. You should note that if I dissolve 10 of these, okay, what am I getting? I'm getting 10 of these. I'm getting 20 of these. All right, so I could get the strontium from one source. Let's say I get strontium from strontium nitrate. And I get the chloride from sodium chloride. Okay, 2 different sources. Now, I would just plug in the concentration of strontium that I have. I get it from there, and plug in the concentration of the chloride from there. Great. And still, I would square it. These are only doubled if I'm adding them in a 1 to 2 ratio. Okay? That is something that causes kids problems perennially. Keep in mind, it's not a real difficult idea. I always say consider the source. Where did it come from? Do I gotta double it? I don't know. Look what they gave you. Is it coming from separate sources that aren't connected, or are they coming from a source that contains a 1 to 2 ratio? And therefore you get 1 to 2. This math, grab a calculator, 1.2 e to the negative 6th times 2.4 e to the negative 6th squared. I got 6.9 e to the negative 18th. Check my math. Always can make mistakes. Not a very product favored reaction. Okay, very much reactant favored. Alright. What does a common solubility question look like? Alright, go ahead. See what we got here. Acidic temperature, lead iodide. The KSP is that. determine the molar solubility of these guys. So now we're kind of, number one, it says molar solubility. At the beginning, this is going to toss kids. What does that mean? That means it is the concentration of stuff that's going to maximum concentration. Pb, 2 plus, I negative. It's what's the moles per liter of this stuff in a max solution at the temperature that you're getting. Keep in mind that K is temperature dependent. Change the temperature, I change the solubility. Alright, let's walk through how this thing sets up. So I'm going to, we haven't had one like this yet. So let's just take a moment and let's see what we got. Let's write the equation out. PBI2 goes to PB2 plus 2I negative. And I always just, maybe it's a comfort thing. Just start with the nice table and what do we got? I put these dashes here because it's comfortable. You know, I can put them in there and think about something else for a second. So what else we got? I got my K value. Alright. So my K value equals the, well, I'm not even going to put the line in there because I don't want to. K equals the concentration of the PB2 plus times the concentration of I negative squared. Alright, I want to know how much of, I'm basically looking for what are my concentrations if I'm dissolving this stuff. If I'm dissolving this stuff, you should be aware that I'm always going to have 2 more of these than these. And you should be aware that does K really care about if it's a lead, if something's in this beaker, does it care if it's a lead ion or iodide ion? Doesn't appear so. Okay? I could add an outside source of lead ions, Pb2 plus. And if I had enough of those guys, guess what's going to happen? These guys will start to precipitate. So it doesn't matter if I got a lot of lead and a little bit of iodide, or a lot of iodide and a little bit of lead. If these 2 numbers together exceed the K value, I'm going to be having, I'm saturated. Okay. If I'm saturated, these 2 numbers together must equal this number by my algorithm. That's what my model's showing. But in this case, because I'm dissolving the lead iodide, these will always be in a 1:2 ratio. So I have nothing to start with. I'm going to start dissolving this stuff. I'm going to get 1 of these for every 2 of these. Alright? Add these together to get the end. It's just x. Add these together to get 2x. Okay. So if my KSP, I'm going to start plugging my values in. Remember, anything that's in the equilibrium line can just go in the end. Can go in there. So I'm going to get 8.3 e to the negative 9th equals concentration of x, concentration of 2x squared. Notice we have a very small K value, but I don't need to work it out just fine. Solve it out. This is going to be a classic math here, which is 4x cubed. You might notice we had a problem like this earlier with that previous presentation where that 4x cubed came in. And 8.3 e to the negative 9th will divide by 4 and raise it to a power of 1/3 for the cube root. Go ahead, give this a run in your calculator. Make sure you can do that. Okay, I got, holding 3 sig figs, 0.00127, and that would be my x value. So the x is kind of like saying when I want molar solubility, I kind of want the x. I don't want the 2x necessarily, but for every 1 of these, I get 1 of these. I want to know how much of this dissolves. And for every 1 of these, 1 of those, so really x is my answer. Make sure you indicate your answer. What's the concentration of x at equilibrium? That's it. What's the concentration of iodide at solution? That would be it. 2 times that. Okay? I'm not going to multiply this times 2. You can do that on your own. That gives me this one. That's going to be this one. They ask for the individual values, so they have them here. If they ask for the molar solubility of lead chloride, you would just give them this answer. Next one. Alright. Another little variation. What's a common anion effect? Okay. So what it means is that if I want to dissolve, let's say silver chloride, AgCl, and they don't really doesn't seem like it matters what ions are present. I could have some sodium ions in here. I could have some lead ions in here. I could have some nitrate ions in here. The algorithm doesn't seem to care what's in there. Except for if I'm dissolving silver chloride in here, I'm using lead chloride, so we'll change it up for that one. In this case, the Ksp for silver chloride would equal the concentration of the silver ions times the concentration of the chloride ions. It doesn't care what's there as long as none of these are there. But if there are some of these already present, then you should be realizing that I have less room in this thing. All right? I don't have enough spots, like a parking lot, and some of them are already taken. Okay? So with that being said, the one that I'm least soluble in will be the one where there's already, now this is lead chloride, the one where there's already some of those present. Sodium fluoride, nope. Sodium chloride, this got a chloride ion. Sodium chloride, this is the answer. Why? We call this because that there is already a common ion present. Okay? There's a math side of this as well. Here's the math on this thing. Alright, common question. Also use multiple choice wise. Calculate the solubility of lead 2 chloride in 0.1. Okay, so 1, we need the Ksp for this thing, and I don't see it on here. I'll have to get it later. But it's how it works out. PbCl2 comes from PbCl, hold on, oh, sorry there, Pb2 plus Cl minus, and there's going to be 2 of them here. Alright, initial stoichiometric ratio n, it says how much, what's my molar solubility, okay, calculate the solubility, they call it molar solubility probably, which really means we want X. Okay. In a lead chloride, which already has a 0.1 molar sodium chloride, now I mentioned that sodium, it doesn't care, but the common ion here is the chloride. So this is initially, now they're giving me an initial concentration. Lead doesn't matter. This is 0, but this has 0.1, because there's one of them in there. 0.1 times 1 is 0.1. Alright, so now I'm going to start dissolving. I got this little beaker here. I got some chlorides in here. And there's some sodiums, that I don't care about those. But I'm going to start dropping in some PbCl2. So when I start dissolving these, I'm going to get 1 Pb and 2 chlorides. And I want to know, based on the algorithm, Ksp, for lead chloride, I know that when my concentration of my lead ions times the concentration of my chloride ions cannot exceed the Ksp value. So again, the beaker doesn't care where the chlorides came from. All it knows is that PbC2 plus chloride minus. I drop one of those guys in there. Okay, so now I got lots of stuff there. It doesn't matter which one it is. I got stuff there. So we're going to gain 2x of this, and we're going to gain, gain x of that guy. We're going to gain x of this one and 2x of this one. That will allow me to say, okay, there's just x, and there's 0.1 plus 2x. Okay, and now that includes everything I have at equilibrium. So the Ksp, I don't know that that's given here. I'm going to pause the video for 2 seconds and I'll grab it. Alright, and magically it appears. Now I got this off of page 3 of our workbook. Right in the beginning I typically have a chart that's got some Ksp values in it, and you should be aware where that's located. Alright, there we go. So now this is 1.5 e to the negative fifth. Now every number should have some meaning. So does that number mean anything? Well, it means it's very much reactant favored. Okay? But if you look at a lot of the other ones we've dealt with, it's actually got a decent amount of solubility. compared to the other guys that are dissolving, equals, plug the number in, x, and then plug this guy in. All right, it's going to be 0.1 plus 2x squared. Now you'll notice that this starts to get a little more complicated. We have a squared x value times an x is cubed, and we've mentioned in the past, an example of this is there a way we get around this math? And if the k is small, then we're going to be using our shortcut. I would be honest with you, I think this might be the only place we use this shortcut, is in a common ion solubility issue. So what we're going to do is basically going to say mathematically that the 0.1 plus 2x is just really, really, really close to just 0.1. And we're not going to get a big difference here. So let's go ahead and do this. It's going to be 1.5 e to the negative fifth equals x times 0.1. I'm going to get rid of that guy. And now it becomes much easier. I do have to square the 0.1 because it's part of that right there. And take a quick moment, calculate out. It's going to be 1.5 e to the negative fifth divided by 1.5. Alright. Nope. It's 1.5 e to the fifth divided by 0.01. And that's the squared value of 0.1. And I'm going to get x equals 0.0015 moles per liter. Now, you should realize that if this was just a 0, then this should be bigger, okay, because there's more room. But with this guy being in there, my solubility goes down. So I'm less soluble in a solution that already contains some chloride ions. Alright, we're at 22 minutes. Let's see here if we can get going quicker here. Oh, there we go. We are done. Thank you very much.